All right. So hi, I hope you're all well. See, it's 17 hours on the dot. We'll start. So a couple of things here, right? I've been meaning to say this, but I don't know how I keep forgetting about this. We have we have a few more, just a few more weeks, I guess, months, I guess we can call them months before we wrap up the year, right? Remember, is it November 6th or something? It's supposed to be the last day of class, and we still have quite a bit to cover. So I was hoping it would accelerate certain things here. But anyways, I don't know if people have any specific questions with regards to what we looked at last time we met. A reminder for those of you that were not around that we've moved the Tuesday slot to Friday, right? So we're meeting day after tomorrow at 8. Take note, thanks. If there are no questions, then I want us to immediately transition to discussion, just a brief discussion of the various techniques that I use to transfer data from peripheral devices to the CPU, right? So we had a discussion about the so-called I/O subsystem. So we set the stage for the so-called I/O subsystem, and we mentioned the fact that it has certain specific roles, certain key functions that make it desirable, I suppose. And the best way of thinking about those different functions, we mentioned that is from the perspective of what it's there to do, right? Remember this idea or notion of peripherals is centered around enhancing the capabilities of the computer system. The enhancement of the capabilities of the computer system will in part involve the use of multiple devices at any given point in time, so multiple peripherals. Interesting question I almost always ask in the sessions we have in almost all the cohorts is, how many components do we think a typical computer system would be able to accommodate at any given point in time? So let's say you have a laptop, a desktop computer, and it has, say, like, let's just use Lighton's, they are here now, they don't want to listen, right? Still using external email accounts. You want to be accepted. Yeah. So take Lighton, for instance, his computer, his laptop, it's a very horrible laptop called the Lenovo IdeaPad 320, has 2 ports. But Lighton made mention of the fact that for him to be able to add additional things for him to be able to add additional peripherals to the computer system, what Lighton does is he uses a hub, right? Oh my goodness, I don't have it here. He uses so-called USB hub, right? The idea behind the so-called USB hub is that it has several ports, right? So if I connect my USB hub, which, by the way, I'm looking at it right now, it has 4 ports, 4 USB ports. It's a combination of USB 2.0 and 3.0, but that's irrelevant. So when I connect my USB hub to my computer system's USB port, one of the ports, the computer automatically perceives itself as being composed of 5 USB ports. Now I could connect another USB hub with additional ports so that I can accommodate additional peripheral devices, so that I can hook up additional peripheral devices to my computer system. A question to think about here, homework. How many devices can we add to a typical computer system? Is there a limit? You understand the question? Is there a limit? Yeah? You understand what I mean? Can you hear me?
Yes, sir.
Is there a limit, right? Wow, that's weird. Question to ask, is there a limit? This thing is getting out of hand. I think we should reorganize the Moodle, right? We should reorganize it like the other courses, not Is organization fine? Should we organize? I don't know. So this is what I mean here, right? So Lighton has this thing here, right? What if Lighton wanted to add more things besides his Maono microphone, besides his printer, besides his 3 external hard disks? Actually, Lighton has 5, but you can only see 3 so far. Besides these, and besides the mouse, what if I wanted to add more things? Let's say I wanted to add an additional 100 peripherals to the computer system. Would I be able to do that? Right? I don't know if people have any responses here. Perhaps not, perhaps maybe not. Those are things to think about, I guess. I don't know. No response. But anyway, so in terms of the features or the characteristics, the key traits associated with so-called I/O subsystem is it must scale, right? It should be scalable enough to accommodate additional devices. It should be implemented and designed in such a manner as to accommodate disparate devices that are capable of handling different types of data, right? So it shouldn't matter whether the data that's going to be processed or that's going to come through from the peripheral is images, maybe just signals or something. If you're scanning something, I guess, I don't know, or if it's textual input, it doesn't matter. It should be able to, should be versatile enough to be able to accommodate all those different types of devices. Right, so we looked at all those different things, and then really narrowed down on the specific functions like timing and control and buffering and all those fancy things. So, like I said, I just want us to quickly finish off the last remaining bit, this idea of the different techniques, right? So far as the design computer systems is concerned, the different techniques that that engineers will tend to take advantage of to facilitate the transfer of data from peripherals to the computer system. It turns out really that there's 3 main methods. There could be more these days, right? But traditionally speaking, there've always been 3 main methods, right? So the first one is more or less like a polling technique, right? Sometimes it's referred as programmed I/O. And then there's interrupt-driven I/O. And then finally, there's direct memory access, right? What I want to draw attention to, our discussion is superficial, but I want to draw attention to why of the intrinsic differences that might come out of all these different techniques here. Everything is centered around how quickly the CPU can perform operations. And to a certain extent, I guess, the complexity of the circuitry required to implement these techniques. Right, so I want you to think about this as we are quickly walking through these different methods here. So we'll start with polling, right? Otherwise called programmed I/O. And the idea behind polling or programmed I/O is the CPU will periodically check to see if there are any I/O operations that need to be performed, right? Originating from whatever peripherals you have connected to a computer system. Right, so there's some routine that's obviously a part of the operating system that will regularly check to see if there's anything that needs to be processed from the peripherals. If not, then the CPU will continue doing its thing. Because remember, fundamentally, the CPU is there to do what? It's there to execute instructions, fundamentally, right? So it will stop executing instructions and check, right? If there's nothing, it continues executing instructions. It continues what it's supposed to be doing. If there's a request, if there's an I/O request, what it does is it pauses, it stops doing whatever it is it was doing, and then it handles the I/O request. So you notice here that this polling technique here, there's some sort of, if you think about it here, there's a bit of, you can look at, you notice that it's pretty easy to automate the process itself, right? The heuristic is simple, right? I guess we can create the algorithm here. It's simple. CPU just probe. If there's an operation pending from any peripheral connected, then the CPU will initiate processing of that operation. Data will obviously be transmitted because remember, peripherals are there to handle data, right? It's either they are handling input data or they're handling outputted data. So data will be transmitted. Otherwise, if there's no operation, then the CPU continues execution of instructions. Very simple heuristic here, right? So regularly, the key thing here, you notice if you compare it with the other techniques, is the CPU regularly check to see if there's anything that needs to be done. As the tradition here, holy crap, that's tradition here, we will leave this up to you as homework, right? But we want you to go and do a bit of research here. Try and see if you can figure out some of the advantages of polling or programmed I/O, right? I'm sure you'll be able to find enough resources out there. And don't just memorize things that you read online, right? Try and understand these pros and cons. This time around, I want us to have a discussion, I guess maybe on Friday, day after tomorrow, to see what sort of things you come across here, right? Think of it, again, from the perspective of computational time required, so far as the CPU is concerned. Everything in computing is centered around computation, right? Resources. Resources in terms of memory and resources in terms of processing power, right? So I'm keen to hear people's thoughts here. Then the next technique, right, an alternative to programmed I/O or an alternative to polling, so-called polling, is what's called interrupt-driven I/O approach. Now, these two techniques are somewhat similar to a certain extent. The only variation, the only difference here is instead of the CPU routinely checking if there's an I/O request that needs its attention, the peripheral, the I/O device, is the one that notifies the CPU that there's something to be done, right? So the signal in this case it originates from the other side, from the peripheral, not from the CPU. And so what will happen here is the CPU typically stop whatever it's doing, right? Once the device notifies it that it requires attention, it will stop what it's doing and save the current state of the CPU. Remember, on the CPU, think of this from the perspective of the memory components on the CPU, so things like the registers, right? If a CPU is processing something, if there's something in the register and it needs to perform some operation by way of interacting with this peripheral device, those components on the CPU would have to be used with whatever data needs to be processed from the peripherals. So what the CPU needs to do here is save the state, the current state, so the state of the registers and everything else, into main memory, right? Process the request, and then once it's done with that, it will retrieve the previous state of the CPU and then continues execution. The only difference here, again, if you compare this with polling, is that
Dr. Lighton, sorry, just there, you have said that the CPU will save the current state to memory and then bring in the current signals coming from the I/O controller.
yes.
Okay, and by memory you refer to the main memory.
Yes, RAM.
Okay, thank you.
Yes. Can be saved in RAM. And by the way, there's some things here, right? The plan, there's something that we haven't done in the past. We'll try and stitch everything together. Once we have a discussion of the main memory, I think it would be nice for us to just have a brief discussion to try and understand exactly what happens when we do certain things on a computer. Like, let's say if you're typing, if you type the letter H, right? Once we discuss memory, I want us to just have a brief discussion about that and to stitch everything together, right? To see exactly how that H gets to be transmitted and how you get to see it on the screen, right? So what I'm trying to say here is, if some of these things are not making sense right now, hopefully once we tie the different bits and pieces together, it should be able to make sense. Just play along for now, right? But if you feel like you need clarification, just feel free and interrupt me. I assure you it will make sense, actually. In the past, what we've done when stitching things together is we've pretty much limited our discussion to the physical components, right? So after our discussion of these high-level functional units associated with the von Neumann architecture, we'll typically have the lab session actually where you put together some desktop, some system unit, right? So you look at the different components in the system unit and then try to put theory into practice anyway. Probably not going to happen this year because of COVID-19, but we'll try and see what we can do. Yeah, normally the tutors would handle that. Great. Okay, again, for this technique, I would like for us to go out there, more homework. Want to look at the disadvantages and the advantages of interrupt-driven I/O. Again, think about the pros and cons from the perspective of computing resources, complexity of the circuitry, I suppose, right? That it's best viewed from that perspective. So the other technique is so-called direct memory access, right? So in this case, what you have is a situation where you have a device that, I think I left out an important part here. Rather than, fundamentally, if you compare it with the other two techniques, rather than have the CPU perform these tedious operations of interacting with the peripheral device, there's a component, I hope we discuss a direct memory access controller somewhere. Okay, it's here, I guess. So you have a DMA controller, a direct memory access controller, which sort of like replaces some of the functionalities associated with the CPU, right? So so what typically happens here is the device, rather than, trying to see here if I've left out some important thing. Let's pause for a little while. I feel like there's a slide missing here. I think there's a slide missing here. I think there is a slide missing here. Anyway, so rather than have the interaction happen between the I/O device and the CPU, right? If you compare it to interrupt-driven I/O and polling, what you have in this case is a situation where you have a separate component, a microchip called the direct memory access controller. So the idea behind this is you now have the device sending data or referencing data or sending data to the memory unit directly without involving the CPU, right? So the role that the CPU would perform in these two approaches would be performed by the direct memory access controller. And you notice here that there are obvious things that are happening here, right? So rather than have the CPU stop whatever it is it was doing, it would continue doing its own thing, and the direct memory access controller would handle the signals involved between the peripheral and the memory unit, right? So the peripheral device will send a request to the DMA, right? The DMA controller. I feel like there's something that I've missed here. Maybe I think we should have a diagram or something. Yeah, we should have a diagram. I think this would be much better. Anyway, so the direct memory access controller takes up the role of the CPU, right? And so transmission of data is done directly from the peripheral device or the I/O device to main memory, right? That way, you realize that the obvious advantage that you have there is that the CPU has enough time to do what it's meant to do, right? Just process instructions. So there's no interruption that takes place. So no need for it to stop whatever it was doing so that it handles the request that is coming in from whatever peripherals you have connected to the computer system. There's no need for it to be interrupted so that it routinely checks if there's any device that requires attention, any device connected to the computer system that requires attention. Right. I think I'll have to include a diagram here to help explain some of these things. I think I should. All right. So three main techniques essentially. Again, what I would like for you to do is to think about these techniques from the perspective of the complexity involved. And you see, I'm giving away the pros and cons, some of the pros and cons here. If you look at this direct memory access approach here, the fact that you have this separate chip here means that you typically have some complex circuitry that would need to accommodate this DMA controller. A complex circuitry means that you need more components, right, on your computer system. So more transistors, for instance, more gates. Right? Compare this with this rudimentary approach where you don't have any additional circuitry that you need to incorporate here. But also, if you look at this from the perspective of compute power here, resources, you notice that there's less resources, there's more resources available because the CPU is not really directly involved in this transfer of data from the peripheral device. Right. Somebody had a concern, a comment?
Oh, yes, I have a question. In trying to understand the DMA in terms of how it helps in most of the work that needs to be done by the CPU by sending data directly to main memory. With the case of programmed I/O and interrupt-driven I/O, we have a case where the CPU is processing instructions, and then it comes across some instructions which want data from the peripheral, and then the signal is sent. For example, in programmed I/O, the signal is sent to a peripheral, a command to get that data, and then begins to check. Now, in terms of how it is facilitating the transfer of data, because we are saying that in the DMA, the CPU is not involved, and data is transferred directly. But in the programmed I/O and also the interrupt-driven I/O, when the CPU checks the I/O controller designed under programmed I/O and it finds some data, does it get that data, send it to main memory, and then that data moves through the bus straight to the CPU to be processed together with the instructions, or does it get the data directly from a programmed I/O controller straight into the registers and then use it? How does the communication take place?
No, and I think this is linked to some questions that someone asked here, and I was a bit hesitant to answer. I can't remember who asked this question to do with memory. You know, there's different instances. Memory is involved, right? It's just that the CPU is not directly involved in sending the signal, right? So, you know, these different instances, data has to eventually find itself in main memory. If you remember our discussion of the CPU here, data and memory are in the same location, right? I don't know if you remember this. Everything has to be fetched from main memory, or sent to main memory. I don't know if I'm answering your question here. So in all these different instances, the data, I mean, it's not like data is being directly transferred from the peripheral to, if you notice, and maybe this is a bad, let me see if I can find, okay, if we had a, so from here, right, from here, let's say you're fetching data here. It doesn't matter which technique you're using here, data will eventually have to get to main memory, right? And then the CPU accesses data from main memory. But what we're saying is the difference here is in the signaling, right? In programmed I/O, when we say the CPU routinely checks, there's a signal that comes from the CPU. So the CPU has to stop whatever it is it's doing and then try and check if there's anything that requires attention so far as the peripherals are concerned. The same thing happens here in interrupt-driven approach. Similar to polling, but the only difference is that the initiation, the signaling is initiated by the device, not by the CPU. So in this approach, you have a routine, a subroutine that constantly checks if there's any device that requires attention. In this case, the device that has some operation that needs to be executed will notify the CPU. But once the signal is sent to the CPU, either one of these cases, data, the transmission of data is going to be moved from the device to main memory. And then it's accessed from main memory. I don't know if I'm answering your question here. But,
yes, sir. Thank you. And then the other question is, in terms of implementing the designs of these different techniques that we use to facilitate data communication, is it possible that one chip can be designed to under all three different types of techniques? That is, the pooling, the direct memory access, and the interrupt, or is it that a specific I/O controller will be designed with a specific method of handling data communication?
Well, so I can only speculate here, but you have to think about some of these things from the perspective of what is feasible, and also what are the implications on the cost. Everything that is being done, so far as computers are concerned, is centered around money, right? Cost. If you want to mass produce a component that you're going to sell at a relatively cheap price, some of the things you have to think about is maybe try and strike a compromise in terms of the complexity of the circuitry. Less complexity means you have fewer components. Fewer components means you spend less money. Right, so in theory, to answer your question, in theory, it might be possible, but that would be very expensive, right? Really expensive, I suppose. For starters, you'd need, I guess, people that are experts at designing. And why would you want to have, I guess, why would you want to have a component that is able to handle the three methods? But it's possible. I think it's possible. It's theoretically possible. I'm speculating here. I'm making an educated guess. It is possible.
Yes. So meaning the question.
And just hold on to your answer. The same question will come up when we start talking about when we look at the memory hierarchy very soon, right? During our discussion with memory hierarchy, what you notice is that we say things like secondary storage, like your hard disk is much slower in comparison to RAM. Registers much faster compared to RAM. So one would ask, why can we not manufacture hard disks that use the same technology that is used in RAM? It's possible, but it would be damn expensive. The amount of money that you pay for you to gain access to, let's say, 2 GB of RAM, 4 GB of RAM, is orders of magnitude higher than the amount of money that you pay for the equivalent size of secondary storage, magnetic tape. Right? So, and I'm sure there are probably computers out there that are implemented in such a way that, and this is where actually SSDs came into play, right? So you have to think about this from the perspective of what is practical, what is cost effective, what is feasible. But money, most of all, money is actually, it's like money is the root of all evil here. Money is the driver of most of these things here. If you're mass producing something, you want to make sure that you produce it at the cheapest possible price. Right? Yes, sorry, I cut you short. I had to say that.
Oh yes, the idea is also, if I know, for example, you gave us a slide where you listed the present I/O controllers available on your machine when you use the command ls pci. So the question is, if I know that, for example, a USB controller, if I know that the USB controller has only has only been designed using programmable I/O, then I would be able to I would be able to know that, okay, then USB devices utilize this type of controller. It will be easy for me to understand different types of devices, different type of peripherals, what type of controller they utilize or on the motherboard, so that for example, I can't be in a state where I'm always unsure if this type of peripheral device uses this type of controller whose method is interrupt driven, because I know specifically to say that, okay, since only one type of controller to scale up the business in marketing, we can't design them using all these different components, but rather we are going to utilize only one method as a facilitating communication. If I know that, then I know that as long as I know that the Ethernet controller over here utilizes interrupt, then I know that every network peripheral will be an example which will fall under that category.
No, but it's a design decision. It's a decision that's made by the manufacturers of the hardware component. We're not saying that it's almost always the case that we're speculating. The only way you'd find out actually is by looking up this information on the manufacturer website or something, right? But we're not saying that it's always the case that it's just hypothetically speaking. We're not saying that an I/O controller that is responsible for handling data coming through a USB port, for instance, will almost always be implemented using polling approach. That's what we're saying. It's a design decision. They get to decide. The people that are manufacturing these components get to decide.
Oh, thank you very much. Now
it's not like it's set in stone.
With that case, then thank you. So in understanding different peripherals, we also have to go to the same manufacturers to check like what method were they using to design this type of controller on this type of specific machine. Then you know that okay, then these types of devices, they utilize that type of controller whose method in this case is maybe DMA. Then the other question.
I mean, the same argument could be made for, if you remember our discussion of ports, right? It's not set in stone. The ports mentioned that there are some printers, there are other versions of printers that would be connected to computer systems via parallel ports. But these days, your average printer, at least a good number of them, are connected to serial ports. USB is a serial port, right? So I'm not saying it's always the case. It's the manufacturers get to decide how these things are going to be, essentially. Yes, the other question?
The other question is why, in terms of programmed I/O, as the CPU is routinely checking, is it because that the CPU routinely checks? That's why they gave it the name programmed I/O. At least on interrupt-driven I/O, I understand why they gave it that name. It's because the I/O controller, when it has a request, it will interrupt the CPU and then send that signal. But in terms of programmed I/O, why did they give it that name?
Well, I wouldn't know. I can only speculate here. When you say programmed I/O, maybe it's making reference to like a subroutine, because it's probably a computer program that will have to routinely check, right? Have the CPU check. So I can only speculate. I don't know why they gave it programmed I/O. But I certainly know why. I can speculate why it's also referred to as a polling, right? Because the CPU constantly poll to see if there's anything that requires attention. But I don't know. Maybe it's because you have this routine that will have to regularly check, so it's programmed. It's an automated process.
Okay, last question for me, sir. In terms of this last statement on this same slide we're having over here, there's a point to say the DMA sends a hold request, and then inside the brackets there's a HLQ to the CPU, and then the last point is the CPU sends a hold acknowledgement. I'm asking if you can just explain a little bit more on that one, sending a hold request, because the CPU is normally involved at the first time when it gives the power to the DMA in order for the DMA to have full control, why it also becomes the master and the CPU the slave, according to the last point you have written over there. It has access to the system bus. But on these other points where you say the DMA sends a hold request, at what point does it send the hold request, and what's that hold request? And then the CPU also sends a hold acknowledgement. Is it when the DMA has done using the system bus, and then that's when those requests happen? And what are those requests?
Right. Yeah, I would have to pause here. I would have to look up this information. I do apologize. I have to look up this information later on. I think we need to have a separate discussion about how the order of events, the sequence of events. Yeah, you're going to have to give me time to look into this, and then we can have a separate conversation. The last point here is a bit iffy. I think there's certain information that is missing. You just look it up, and then we can have a review session or something.
All right, thank you, sir.
Mm-hmm. Any other questions? Trying to figure out what's happening here. I think there's a slide missing. Anyway, so right. So I thought we have a bit of time for us to start our discussion of computer memory, right? I think we're slightly behind here. So trying to think. But if there are no questions, let's do this. Friday, we can have I'll look this up, and then Friday we can have a conversation around this, especially. Because it turns out that for you to be able to figure out or to make sense out of some of the pros and cons that you come across in literature, you need to understand the sequence of events, what actually happens. Okay, so lecture series number 11 is it's computer memory overview and primary memory. So what we do is we briefly have a discussion of just very basic of computer memory, and then we combine this discussion with so-called primary memory. And what we've done in the past is we discuss primary and secondary memory differently, right? Just because they have different characteristics and their functions are kind of different. Anyway, so the outline is as follows, right? We'll start off by just the very basics. We want to understand the relationship that exists between the performance of a typical computer system and in the relationship to computer memory, right? We'll revisit some measurements that we introduced when we were looking at data rates, more like a refresher, actually. And then we'll look at specific aspects associated with memory, right? And this is linked to the so-called memory hierarchy. So you notice that once we start looking at these different memory components, you notice that there are certain traits or certain aspects that tend to change depending on which memory component you're discussing, right? So things like size, cost, performance, right? And then we will discuss specific categories associated with so-called primary memory. And specifically what we focus on is CPU cache, RAM, right, which is what we're calling primary memory, and so-called virtual memory. Now you notice here that there's a primary memory component that we've deliberately left out here. These are registers. We've left them out because we've already had a separate conversation about registers. But they'll manifest themselves in the memory hierarchy. You see them there. And in fact, they're usually high up the hierarchy, right? Much faster than things like RAM and virtual memory, for instance. Okay, so this has become second nature here, right? A reminder that we are studying this thing we're calling a computer system. And also another reminder that we've actually looked at almost all but one component, one high-level functional, one high-level von Neumann model functional unit, right, which is a memory unit. So this is what we're discussing, memory unit. And again, some of the things we're going to be discussing with regards to memory, the memory unit would actually apply to things like registers, right? Yes, we know registers sit on the CPU, but it's also a memory component. It's considered primary memory. Same goes for, is it level 1 cache and level 2 cache? All of these will sit on the CPU chip itself. All right. Right. So to remind you that there's a reason why we mentioned it. There's a reason why we need registers on the CPU chip, right? Because ideally, access to so-called RAM is usually much slower, right? The turnaround time, the distance that would have to be covered for the CPU to fetch content from RAM and then take it back to the CPU for processing is too long, right? So it slows down the computer. What do you do to make that process much faster? You have faster memory components on the CPU, so-called registers, right? So mentioned that registers will provide you with quick access to storage, but because of the size, because of the form factor of the CPU itself, you have very few registers on the CPU. Enough to be able to temporarily hold instructions that are being executed at that point in time. Remember the fetch, decode, execute cycle? And we simplified our conversation or discussion of the fetch, decode, execute cycle, right? We're looking at a single cycle where only a single instruction is being executed on the CPU. But in actual fact, you typically have a number of instructions that are being executed, right? So one instruction is in the instruction fetch stage, the other one is in the instruction decode stage, the other one is in the execute stage. But something else we want to remind ourselves of is the role of the most widely used type of primary memory, so-called RAM. It's a staging area for program instructions. Every time you want to execute an application on your computer, the first thing that happens is it's loaded into RAM. And then from RAM, the CPU will start fetching or executing individual instructions associated with that program. Right? This we've mentioned. So immediately notice here that there are certain key things that are going to come out of here, right? Things like the size would probably matter or something, which is why when you're buying a computer, for instance, one of the things you tend to look at here is, how much space does it have? And I don't know if most people just go with the crowd, right? No, you should buy a 1 terabyte, a computer that has 1 terabyte. It's better that way, right? But usually when you're purchasing a computer, you typically have a section which has these aspects or attributes, right? What you will notice is that in almost all the case, they will explicitly specify the different types of primary memory, right? So things like how much CPU cache is built into that particular piece of hardware or computer system, how much memory or RAM that computer system has. This is all primary memory, right? The only thing that is rarely specified, actually, last time I checked, most manufacturer websites will not tell you, well, they won't really give you a breakdown of things like level 1 cache and level 2 cache or something, but they'll just give you this holistic number to say it has 8 megabyte of cache, it has this much RAM, right? Yeah, if you want to find out details of specifics of registers, I guess you'd have to dig deep and find out that information. But bottom line here is that all of these things are associated with the performance of the computer. But remember that during our discussion of the central processing unit, we highlighted aspects specific to the CPU that influence the computing power of the computer system. And so what we're saying is that these things we've highlighted here will complement the aspects that we raised insofar as the CPU is concerned. So the clock speed, the number of cores associated with the CPU itself, the type of the CPU processor, which generation it is, and of course the cache size on the CPU itself. Again, what we're saying is that the amount of RAM that you have, the amount of primary memory that you have access to, together with the specific details associated with the central processing unit will influence how quickly you're able to process instructions on that computer system. And usually, a rule of thumb is the higher the better, I suppose. You'd be okay if you go for the higher the better. Higher clock speed, more CPU cores, larger value for RAM, right? These are all good things. Right, so RAM, like I said. And this is highlighted here because, sure, our discussion here is primary memory, but storage is also memory, right? But it's a specific type of memory, persistent storage, right? And much slower nonetheless. Right, so again, collectively, the things that we tend to influence the performance of the computer system, details associated with the CPU, capacity of the RAM, speed of the RAM, the speed of the hard disk, right? To a certain extent, maybe the capacity of the hard disk as well. This would be in instances where maybe you might want to convert some aspect of your hard disk, I guess, into virtual memory or something. Right, so, but remember that when we're talking about memory, the measurable we're making reference to is typically data and instructions. And all of these things, both data and instructions, are typically measured in bytes, right? They are stored in bits as ones and zeros on a computer system, but from point of view of human beings, for you to be able to make better sense out of what you're storing, we normally visualize them in bytes, right? This thing that we discussed in lecture series number 9 here, when we're looking at data rates. So this has, I guess, become second nature here, the conversion here. I hope this has stuck into our heads by now. The only thing you have to remember here is this value, the 1024, and of course the order of these different units. Is this making sense? So on your typical computer system, these are some of the things that you'd come across. So the screenshot is coming from, I guess it should be from my, I think, pad, right? Showing you different values associated with different memory components, right? So I guess usage of total amount of memory that is there, used and available, disk cache, the buffers that are there. I'm not sure which one would be swap space, which is like virtual memory, right? So these are typically the visualization, the way that you get to look at these quantities is different depending on what type of operating system you're using, but the concept is the same. In Windows, last time I checked, if you just go to, you right click my computer icon and you go to properties, you should be able to see some of these things, right? Like memory, you should be able to see most of these things that are appearing here. So how much RAM you have, how much storage space you have. I do believe for you to be able to see details associated with, let's say, cache size, for instance, you probably have to feed it around a little. You wouldn't have access to those things if you just right click them, my computer icon or something. All right, so I hope this is making sense, by the way.
Yes, sir.
Okay.
Yes, sir.
Right. But to better understand these different memory components here, right? Irrespective of whether you're looking at secondary storage, like your hard disk, your magnetic storage, your SSD, solid state drives, or whether you're making reference to virtual memory or CPU cache, or perhaps registers, they're best perceived by taking into account these three aspects. How quickly data can be transmitted to and from the component. How much data can you lump onto that particular component? And how much it costs, how much it would cost you, I guess, by taking into account a particular unit, right, a measurable unit or something. So cost, capacity, speed. There's some of the important aspects to take into account as you're looking at these different memory components. And what you will notice here is that, and this is a rough estimate here, what you will notice is that there are certain interesting things that happen as you are moving away from the CPU, right? The speed or the technology that is used to implement the memory components that you find on the CPU chip will result in a much faster memory component in comparison to memory component that is further away from the CPU. So registers are obviously much faster than cache, or CPU cache. Cache would be much faster than RAM. RAM would be much faster than secondary storage. For the most part, it's not always the case, but for the most part. I wouldn't be surprised if there are people that have implemented or that would typically use a computer system where the speed of the secondary storage is more or less the same as RAM. It is possible in theory. It would be more expensive anyway. Right, so speed increases. The capacity also increases. And it makes sense that the capacity increases, by the way, because when you have a component being slotted on the CPU, for instance, because of the size, the form factor of the CPU, you expect it makes logical sense that the memory unit that you have on the CPU would be significantly smaller than something that's not on the CPU, right? It's expensive. But also, another way of looking at this is the sort of what exactly is being stored in these memory components, right? If you think about it, when you're making reference to the CPU here, what you are handling are individual instructions and data, small in size, right? So very, very soon you notice that once we start looking at MIPS, for instance, we will make mention of the fact that MIPS makes use of the 2-bit registers or something. So compare that with, compare that particular size of an instruction, that is the 2-bit in size, with the size of an application that you'd load into RAM, right? This explains why, partially explains or in part explains why RAM will be significantly larger than cache or registers. And by the way, here we are in terms of cache. Specifically, I want to be very careful here. I'm specifically making reference to level, traditionally speaking, level 1 and level 2 cache are stored on, they are found on the actual CPU chip. Depending, again, this is a design decision. The manufacturers will have level 3 cache not on the CPU per se, but these days it's not uncommon to have both level or all the levels actually sitting on the CPU. The only difference that is usually there is that each of the separate cores will have like a separate level 1 and level 2 cache, but they'll share the level 3 cache. Right? But that's not important anyways. Right. Again, in terms of cost here, notice that the cost will typically decrease as you're moving away from the CPU. So the memory components that you find on the CPU are usually much more expensive than secondary storage, for instance, or RAM, right? And again, these are just approximate values, but they just trying to showcase to you that if you look at this from perspective, moving on from the CPU, cost decreases, speed, well, actually everything is decreasing actually. Speed decreases, capacity on the other hand increases. Right. So obviously, I mean, if you look at this from a completely different aspect, about these are the aspects we're talking about here. So speed decreases, capacity increases, cost decreases. And so another way of looking at things like speed here is, okay, we are loosely looking at speed here, the speed of the data rates associated with the particular component itself. And if you use logic, it makes sense that even if we're using the same technology to implement, let's say, CPU cache and RAM, the speed will still decrease. Why? Because of the latency. CPU to RAM, the round trip that it makes. I don't know if I'm making sense here. So this behavior here we're just describing take us to this nice memory hierarchy here. If you look at all the different types of memory components, this is sort of behavior associated with the various characteristics. So capacity or size, the speed, the cost, right? You come up with this sort of pyramid here. Something we haven't yet discussed here is this notion of whether or not a particular memory component is persistent, right? So typically, virtually all primary memory is not persistent storage, right? So when power is not being supplied to the memory component, data is erased, right? So making reference to here, notice here, power has to be on for you to be able to access data from that memory component. As soon as you switch off power, data is not available. Now I know what you're thinking here. Well, what about the BIOS, right? Yeah. What about the BIOS? When we switch off power, what happens? Anyone has an answer for that?
Or the standby, sir.
What?
When
No,
you put your computer to sleep.
No, the BIOS. We're saying, listen, what we're saying here is that this memory hierarchy here is taking into account everything. Both. In fact, you could look at the top here as being composed of primary memory, right? The base here is secondary memory, right? So size increases, capacity, size or capacity increases. As you move down the pyramid here, you'll be able to retain the data, even if you are not supplying power to the component. But for primary memory, things like RAM, CPU cache, registers, the moment you switch off the machine, gone. Now the question I have for you is, the BIOS is read-only memory, right? It's primary memory. Why is it that we'll still have access to the program in the BIOS, the one that's embedded within the BIOS itself? When we switch off the machine, we still find it there. Why?
Is it because it's powered by a CMOS battery, even
Yes,
if
so
the machine...
thank you. So there is still power by way of the battery, the CMOS battery. Yeah, excellent answer. That's what we're looking for. Right, so the memory hierarchy, right? This will come back. So our discussion for primary memory is the top layer, yes, for now. We are going to look at the top layer by looking at those specific memory components: CPU cache, RAM, ROM, virtual memory. And then in the next lecture series, we get to look at the bottom part, which is secondary storage. So we get to look at the various types of secondary storage components: network storage devices, SSD, magnetic tapes, and different variations of magnetic tapes, right? All those, the good stuff here. So just to, let me see if we have, let me see if we can quickly wrap up this or leave it till tomorrow. Yes, we can do this, right? Up to here. Yeah, finish off the hack. Right, so again, the primary memory components, again, this is not set in storage, but for the most part, primary memory is used to temporarily store data. So data in primary memory is temporarily stored in there. In other words, it's transient. The moment you stop supplying power to the component, data is not returned, it goes away. This is why when you're working on your computer and there's no power, say, oh my God, I didn't save the data, it's gone, right? Because it's not a persistent store. With the exception of certain components like ROM, obviously, right? So, well, typically speaking, you typically have a battery supplying power, you know. What it's used to do, what primary memory is used for is to just store data and instructions, right? So in this case, like if you look at RAM, for instance, the moment you double click the application, both the data that you're manipulating using that application and the instructions associated with that application or part of the instructions are going to be loaded into a component like RAM, for instance. And then your fetch decode execute cycle is initiated. But on the other hand, if you look at secondary storage, otherwise called computer storage, data is persistent, right? It doesn't matter whether or not there's no power being supplied, so you can move around with your flash and your data is still going to be there, but it's persistent. And typically, so want to draw a distinction here because if you remember, when we're looking at IO devices, we raised the issue of storage devices. It's usually a bit confusing here. We always want to rub it in when we have this conversation to emphasize the fact that data is actually stored on the storage medium. The storage device is it's an electronic component that is used to facilitate access to what you're storing on the storage medium. So typically, there's a thin line here because most storage devices will be, the storage medium will typically be embedded within the storage device. Like if your flash disk, if you were to open up your flash disk, for instance, it's called the flash drive. Inside there, you'll find a storage medium. That's where the data is actually written to or read from. The same goes for your hard drive, right? Some people say it's a hard disk, some people say it's a hard drive, doesn't matter. But typically, the medium itself, the hard disk, is embedded within the hard drive. It's inside there. So the mechanical component, the drive itself will have components that allow it to access various types of data stored on the storage medium, right? So two different things here, storage medium and storage device. The storage device would be what we're making reference to when we're looking at different types of IO devices, communication devices, storage devices, input devices, output devices, right? So the storage devices obviously can be internal, external, remote, right? And we'll discuss this when we look at computer storage or secondary storage. The internal type would be the internal hard disk that comes with the computer once you purchase it. External device, external drive would be something like your flash drive, for instance, or something that you buy off of the store or something. Or it can be remote. So it can be cloud-based like Dropbox or Google Drive, right? And I wonder if the name Google Drive also took into account the storage device type thing here. But anyways, and the way that you gain access to secondary storage, obviously on a computer, is on operating systems such as Windows. You typically gain access to different types of storage by the drive letters, right? My C, where's my the C drive, right? D drive. I don't know if if you partition your hard disk, you typically have multiple drives, but you gain access to them using letters. It's not the case for Linux. Access is somewhat different. Doesn't matter nonetheless. Right. So when we meet Tuesday morning, we will start our discussion of RAM and ROM, so primary memory, and then we will start looking at these other different memory components. So we're going to go through this journey here. We skip registers. I don't know if we discussed we skip registers. We start with the top going down here, all the way up to virtual memory. Unless if there are any specific questions. Let's see if I wonder if people are still online actually. Any questions?
So
Yes.
That battery you're talking about, is it the one that is slotted in on the motherboard? That's more round flat battery.
Well, I don't know these days how they look like, I'm sure, but traditionally they have been round. Yeah, I see most batteries usually round in color, shape, sorry. Depends on so now the thing to think about here is what about on your phone? I don't know, right? So, but yeah, it's usually on your normal desktop computer, it would be circular in shape like so. I'm not sure about smartphones. I'm sure it's probably much smaller, right? Smartphones also have BIOS, so it's bound to be a battery in there. Any other questions? So yes, the answer is yes, sir.
Thank you, sir.
Any other questions? Tired. I'm tired. See you on Friday, 8 hours. Maybe we should move the class to 7, right? I don't know. Or 6 or something. Sorry? 5?
No, sir.
See you at 8 on Friday. Thank you. Bye.